All right, Beer's Law Lab, and Beer Lambert is the name for it. I'll see here. Beer's Law Lab, Dry Lab. Okay, we have not. This is like one of the first ones we're going to do is a dry lab. I'm going to have you try and do this the best you can. There's a couple of reasons. This is something that is not really in any lesson chapters in the Zoom doll. I mean, you can put it in the chapter 7, or you can also put it kind of with last semester with Molarity. But anyway, there is a device called a spectrophotometer. Spectrophotometer. You're going to see the word in a minute. Or there's also one like this, a computerized one called a colorimeter. Colorimeter or spectrophotometer. The spectrophotometer is a more expensive, the advanced version. And inside it you put what's called a cuvette. Inside here, what does it do? Well, this device actually shoots 4 different wavelengths of light, kind of like a laser pointer. A laser pointer is one pure color of light. So this gives you one pure color of light, which would be kind of like violet, blue, green, or red. Violet, blue, green, red. There are 4 colors, and instead of writing the name of the color, V, B, green, red, they have written the wavelengths: nanometers, 430, 470, 585, 635. Well, anyway, the way it works is, what in the world is this? Well, this is something. First, I'll show you the equation for Beer's law. It looks like this. This is called absorbance. Is equal to ABC. This is called the molar absorptivity constant. B is the path length, or actually, in the colorimeter, let me find that again. It's the width of the cuvette. There it is. And you see it's a square cuvette. So usually it's 1 centimeter. That looks like it's about 1 centimeter also. So 1 centimeter, it usually is almost always used as 1 centimeter. It's the path length, in this case it's 1 centimeter of cuvette. C-U-V-E-T-T-E. C is, guess what? Even though it's a small letter C, it's the concentration. It means molarity. Mole per liter. It's molarity. So you could have put that. That would probably be a better way to write it, but oh well, with molarity. But it is molarity. It used to be called A equals ABC, but they recently started using the word, the symbol, the lowercase Greek E, epsilon. Okay. All right. What in the world is this? What is Beer's law? Oh, there's something really cool. I don't have the equipment to show you this, but I would show you if we were in class. Well, anyway, I'll get to it. I'll explain it to you and show you. Well, it turns out that some scientists, I guess Beer and Lambert, were the ones who discovered this. But Beer, I don't know his first name, discovered there's something interesting about any chemical that has a color. Now, I have a few of them here to show you. This contains nickel, and you can tell that color is green. Ni+2 is a green color. This one contains, what is rust orange? It is iron, okay? Iron nitrate. Fe+3 gives you an orange color. Cobalt+2 gives you a red color. Okay, there's many of these that have colors. Well, there aren't as many as there are. Most chemicals look like this. Like, what is that? Wait a minute, it's sodium hydroxide. But look, it looks just like it's water, just like salt water. So almost every chemical you dissolve in water has no color. Well, anyway, but some do have a color. And as scientists, well, Beer and others, realized that you can actually find the molarity of a chemical by simply shooting a light through it. Now, isn't that neat? If you shoot a light through a chemical, you can, based on what light comes out, the amount that comes out, you can tell what the molarity of it is. Now, it takes a lab little procedure to do that. So, anyway, start off, we're going to look on here, and it says, the beginning of the notes, just talk about the visible spectrum. You know, white light. White light, or from the sun, light from the sun, is composed of all the colors of the rainbow. Now, even though we say Roy G. Biv, you know, we talked about in an earlier chapter that really there's other colors in between. There's many different colors. You can blend from infrared invisible that comes into the red, really red, you know, then kind of reddish orange and yellow, blue to green, and so forth. You can add some other colors in there, like the word magenta. Magenta, that's a neat one. What's another color? Cyan is one, kind of in between green and blue. Magenta is kind of a pinkish kind of a color that you see, pinkish purplish color. But anyway, so here we have Roy G. Biv. We're going to talk about that in a minute. But all of those combine to give you white light. Now the sun, when you look at the sun, it looks like it's yellow. Because actually, the reason why it looks yellow is a little bit based on Beer's law, you could say, I guess, but because when it passes through the atmosphere, some of those wavelengths are blocked, and the ones that pass through give the appearance of the blue that you see. That's weird? So we leave out some of these, and we get blue, a blue sky, and the sun looks like it's yellow. But if you go beyond the atmosphere, the sun would be like stars at night, just completely just white light. That's how it would look. Now through a prism or through a diffraction grating, as we talked about in the last, chapter 7, not last chapter, but earlier, that will come out and it will give you the white light comes in, and then out comes the rainbow, Roy G. Biv. It separates it, spreads out the wavelengths. Okay. Well, for light, it's different than pigment colors. Okay, like when I say that, what I mean is, when I say pigments, think about finger painting. Okay, when you're finger painting, if I mix together red and blue, I'll mix them all up and I get purple or violet. Okay, or if I mix red and yellow, I'll get orange. Okay, you know how that works with the three primary colors: red, blue, and yellow, right? No, yeah, red, blue, yellow. Aren't those the three primary? Okay, yeah. Okay, sorry. You can make green with blue, with yellow, and yellow and blue get green. We know all that stuff. Well, hopefully I know it. Okay, but we know all that. Well, that's true with pigments. Okay, and you probably have also heard someone say with pigments, like my shirt is blue. What that means is all the colors of light are striking my shirt, but and then when it does, it absorbs all the colors of the wave of the rainbow except for the blue, the particular blue you see here, the light blue, whatever, and that blue is reflected. So that's how it works for pigments. For solids, that they take the sunlight, electrons excited, and all that, and what they release is they release the energy, the wavelengths that are not absorbed, okay, by the material. Well, it's different in a solution, okay, and let me show you a little picture. I'll kind of try and draw how this would work. So I'm going to do this. I'm also going to draw something called a color wheel. There is something called a color wheel. There may be one somewhere in your textbook. You certainly can find one online. And if you've ever seen it, what it is they've made, it's based on, it works with solutions. I'll say solutions. It probably would be the same for gases, but any solution like the ones that are green, blue, and all that. Well, what happens is, I made my own little color wheel this way. 1, 2, 3, 4. Uh-oh, I didn't do too good with that, did I? 1, 2, 3. Well, that's close enough. Now, what I'm going to do on the color wheel, I'm going to label these colors as I go around it. I guess I'll do it over. I had to erase that one, so oh well. Can I do better? 1, 2, 3. This time I'm I tried to on the target. Oh well. Okay, now I'm going to put in Roy G. Biv. So red, orange, yellow, green. But guess what? I'm going to put cyan, then blue. Uh-oh, cyan. Who is that? Blue. Then I'm going to put the like indigo and violet. Or blue, cyan. There is another color. I'm forgetting another one. I didn't write it on this one. Oh no. Or did I? Let me see. Magenta, red, orange. No. I'll have to find out where I did write it, but this will kind of work. Anyway, the point of this is if you pick a color, now blue, cyan could pretty much be blue also, but it's in between blue and green. But what you do is this, like a turquoise color. So here's the deal. I'll explain this in a minute. It works for these two for sure. This is violet, purple, and this is green. And then here you see orange, and this side you see blue. Well, here's a neat thing about this. Watch this, and I'll tell you. You do not have to memorize these colors or anything like that, okay? But here's what happens. If this solution, let's just say that I'm going to put all the white light through it. I'm putting a white light. I'm shining it into this container. Now, white light means I'm putting all the colors, Roy, G, Biv. All those wavelengths are going through it. But what comes out on the other side? Okay, so let me see, do I have some chalk here? I can have fun with the colors. So let's go to the one that was green that I showed you. Well, let's go, I tell you what. Instead, let's make it purple, because that'll be a little bit more interesting here. All right, so let's say that the solution looks to be purple. And by the way, is there a solution that has a purple color? You might say, oh yes, purple manganate, permanganate has a purple color. Well, according to this theory, what happens is, when you pass all the wavelengths of light, white light, in through this purple solution, the molecules of permanganate that are in there, they absorb the green. Now, so if it appears purple, we'll say violet or purple, that means opposite on the color wheel. This is the wavelength that it pretty much will absorb, something in the green area. I mean, it can be closer to yellow-green or kind of a bluish-green, cyan, around there. But if it looks purple, it will be green. Now, you could further divide this up into many different kinds of purple and different shades. But again, like I said, you have many different shades of green on the opposite side of the color wheel that you'll get. So if it appears violet, what that means is it is absorbing in Roy G Biv, but outside, we'll just make it easier, comes only Roy Biv. Where's G? There is no G. So what happens is all the remaining colors of the spectrum that are passing through, all the wavelengths, Roy, red, orange, yellow, blue, indigo, violet, they combine, and the way they combine, it turns out appearing purple. Now that's strange. Now again, with finger paint, that doesn't work. You put red, orange, yellow, blue, indigo, violet, you're not going to get purple. But with light, it does. So energy is going in. Energy is being absorbed by these molecules. Remember, there's certain wavelengths of energy, certain electron configuration levels that go up and down, all that. So only certain quantized levels are absorbed by this, and they move the electrons. The other ones just pass right through. So as a result, the ones that pass through, when they combine, and they're early in here, the ones that are shining out, are these combined, and they look purple. Now, if something appears violet, that means it's absorbing the opposite, pretty much green light. If it appears green, it's absorbing purple light. So the one that we saw earlier, the nickel that I held up a moment ago, this is absorbing the mainly purple wavelengths of light. The other wavelengths are going through, and they're appearing to be, how do you say it? Green. Okay, what a weird thing. And then orange and blue, I always like that one because that's my school Auburn color. But yeah, blue, opposite. So that one, that's kind of interesting. Now red, opposite red is cyan. It can also be kind of a blue. I mean, like I said, it's a bluish color. I mean, there can be a red light. In fact, I think I did one of these in the AP Readiness. I did one of these at UCLA. Maybe you saw that one or not, but I had to shine. I had a red material, cobalt, and so the light I had to shine through it. The closest one was like a blue color because it's really close to being blue. I mean, red and blue almost. It's a type of red. So this is not a perfect color wheel. To be perfect, you'd have to have the exact number of the wavelength. There's many different numbers along here for different kinds of red. Brick red, dark red, orange red, and all that. So okay, this is just to give you an estimation right here. All right. So I also have another one here that Oh, this one has blue and yellow and blue magenta. Blue, yellow. Yeah. We'll see. I know, so it's not perfect. My little thing doesn't work. But there's another little one on your worksheet, and yours, I think yours is colored. And so, well, the red cyan, that one works. Those are opposite. And green and magenta. It says magenta for green, but it's like more like a purple. I don't know. I have to see. Did I mess up with the yellow? The blue to yellow. Oh well, don't worry about that part. Okay. Well, anyway, what it says here, a color wheel below it. Color wheel shows the complementary colors of light absorbed and light transmitted. So some wavelengths are absorbed, some are transmitted. A solution, it says yellow, is absorbing blue light and transmitting all remaining colors. So I'm saying that, if it looks yellow, it's kind of an indigo, is what I put. But I mean, again, you could also go to there and say yellow light, it's kind of in between, like blue. So that still kind of works with these opposite sides here. But it's more in the yellow range, in the blue range. But it says if it absorbs yellow, if it appears yellow, it will be absorbing like a blue light, okay? Or on mine, it would be an orange or orange light. If it appears, I'm sorry, I got backwards. If it appears yellow, it's absorbing like indigo or blue, kind of a purplish or blue. Is what, according to what my drawing here. All right, colored chemical solutions can be analyzed by passing a specific wavelength of light through them and then measuring the transmittance of that wavelength of light. Now, transmittance, there's a little equation. You don't really have to worry about this so much, but you could see it pop up sometime. I don't know. Probably not on AP. But I is the intensity of the light, like original intensity. And then the final intensity, the transmitted intensity, we put I. I'll put an IF there. On your paper, it just says IO, then it has a bunch of X's, like going through the solution. I don't know why I did that. IO, and then IF. Initial intensity and final intensity. Okay, so let's just give you an example of this one again. So if it's purple, that means it's absorbing green light. So let me get a green one out here. So it is absorbing the green wavelength. So if I want to measure how this solution, according to the Beer's Law lab, what I'm going to do, a light probably somewhere in the green area is the one I want to shoot through this. So I'm going to start off. Maybe I'll take away this for now. We don't really care about the other colors in Roy G. Biv. All we care about is the one that's being absorbed, which is mainly green. So let's just say you get this green light, here, and you shine it through the purple light, through the purple. Okay, so it's mostly being absorbed. Now let's say that on this side you just get like just a really, really small intensity. Now remember, intensity of light is on a wave. It's the amplitude. How bright is the light? Okay, remember we talked about that, like shining a brighter light or a louder sound will be a more amplified amplitude. Okay, so here we'll say this was the intensity of the light before, and this is the intensity after. Okay, so what they measure is the percent. What percent is absorbed by that? Like if you start off, let me see. This is actually transmittance, percent transmittance. I'm sorry. So transmittance is about 0% for that color green. I mean, we'll say a little bit gets through. So let's just say that, I don't know. I'll just say if it was 10% how about 2% transmittance? That means 2 out of 100. So here it's 100%, but only 2 came out. But don't worry about measuring the intensity of the light, and luminous intensity is not a big deal. But we normally talk about transmittance as a percentage. So 0% transmittance would mean you have 100% absorbance. That should make sense. Okay, so whatever your percent is, I mean, if you have these 100%, 0% transmittance is 100% absorbance. Now, let me show you the graph below. Okay, so here's a graph. Yeah, don't even worry about that IO thing. I was going to say that the transmitted percentage would be I final divided by I initial times 100. That would equal percent transmittance of the light. You're not going to see this anywhere, AP, don't worry. But there's a math way to get the percent transmittance. But the good thing is, the little computer that I do, it will do it for you. It will just tell you what the percent transmittance is. So if I draw a graph, and I guess I'm going to have to erase this one here. Oh, I'm going to come back to that one for now. Below that, it says absorbance is, oh no, the natural log of the initial divided by the final. Okay, absorbance is calculated with a logarithm. And you don't even have to really worry about that either. Okay? But here's how the graph, here's something you should be aware of. If I were to graph, I'm going to do the right one first. It says transmittance versus wavelength. There are two graphs I want you to think of. On the left, absorbance versus wavelength, and transmittance versus wavelength. So here I'll put transmittance, and here I'm going to put wavelength. All right, so before I go any further, let's say we are doing the experiment. Here is what you're supposed to do if we have the correct equipment. There is something called a spectrophotometer. All right, spectrophotometer. Now, this one that I have is a simple one that only gives you 4 possible wavelengths from 430 all the way up to 635. Yeah, 430 to 635. But a good instrument, you could put any number like a dial. I could put 430, 431, 432, 433. You put any possible wavelengths. So we might just say that over here might be 400, and right here might be 700. And let's just say that with this machine, it's going to put every possible wavelength and shine it through this purple light. So step 1 in a Beer's Law experiment, if you have the right equipment, is that you would check every single wavelength. Now with the computers, that can be done a lot faster. But if not, the old-fashioned way, you'd put in, maybe you'd check just 10 of them, or 15 or 20, or maybe everybody in class would do 10 different ones, and we'd find out who has the best. Now, how would you know the best? Well, what you do is you graph it. You graph at this wavelength, so at 400 there'll be nothing, because that's probably invisible anyway, and 700 there'll be nothing. But you're going to end up getting a curve like that. You're going to get a curve, a bell curve. If you put every possible wavelength of light, so say that means not just green, so red, orange, yellow, green, blue, indigo, violet, cyan, magenta, brick red, orange red, any color, midnight blue, anything, navy blue, any colors you can think of, they all have a number. So let's say you put all the numbers in, you're going to get a graph that looks like this. Now, oh no, you're not going to get a graph that looks like this. Bad fella. I just told you, I hate that I just told you to draw it that way. What we did was absorbance, but I want to do transmittance first because it makes more sense, I think. You're going to get, you're going to get an upside down bell curve. I'm very sorry. Here's what it means. This upside down curve means all of this color of light, almost all of it passes through 100%. Like that will be 100% at the top. So almost all the colors pass through 100%. But one color right here, there is a wavelength of light. One color does not pass through 100%. Now, for green, let's just see if I can look at my little dial. I'll make up a number here. Oh, well, I wonder if I should use the one that's going to be in the lab too. Well, I'll just use the one on this one for now, because we're not going to be doing a purple liquid. But for green, 565. So let's just say that this is 565, the lowest point. So in other words, green almost does not pass through at all. I'm so sorry that I drew it upside down. Percent transmitted, here's 100%, here is 0%. So it's almost close to 0 when you get 565 nanometer light. But any other colors, 560, 40, 30, 20, 10, all the way to 400, all these all go almost all the way through. So you can see, now here's another neat thing. You don't have to have only green light in this lab. You could use a different color if you wanted to, but that's just the best one. This is the optimal wavelength. the optimal wavelength would be the one that's the lowest on the transmittance. Now, here's why I drew it wrong a moment ago, because the opposite of this would be absorbance. Absorbance versus wavelength would go down here. Yeah, that fits. And it will be just a mirror image of that. And let's just say it had the same numbers from 400 all the way to 700. Okay, so these graphs they could give you on an AP exam. They could give you this graph and say, tell me, what is the optimal wavelength? It could be a multiple choice question. What's the optimal wavelength? If it's transmittance, then you go there. If it's absorbance, you go to the very highest point. And guess what? I mean, it'll probably be obvious, even if they gave you either one, you go to the most extreme point. That is the optimal wavelength. At this wavelength of light, almost none of it transmits. Almost all of it is absorbed. Now, to make things a little bit more crazy, and I guess, I don't know why they complicate it this way. Probably because with mathematical, it just works easier. It would have been nice to say, oh, here is, it only has, pretend if that were 2% transmittance, that means, oh, that would mean 98% absorbance. Well, unfortunately, they don't put the percent absorbance. They put something else. They do a math function to it. And the actual absorbance is, actually it's on the paper here, it's the natural log of the initial intensity divided by the final intensity, the natural log of it. And so anyway, don't even worry about it, but just know that you're going to get a fractional number. So usually the absorbance, like a high absorbance, was, just pretend that was 0.700, and down here was like, you know, 0.000 or 001 or something down near here. So the absorbance is going to be like 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.10. You're going to get numbers that look like that. Okay, somewhere between 0 and 1. It's because it's not exactly absorbance. You don't have to worry about getting that or anything. You don't even have to memorize the color wheel. You should just know that, let's see, that whatever color appears, like if it appears purple, it's absorbing a different color wavelength. And to find that out, you can look at a color wheel to find that out. They would give you a real color wheel if they did on the AP. They don't expect you to memorize it, but my little color wheel kind of works out. If I need to alter it, I'll let you know. I'll see, but that's worked for most colors for me. Now, okay, so back to this again. So the optimal wavelength would be here. On the AP, they could ask you, given this graph, what is the optimal wavelength for this purple solution? And you look and say, oh, it would be this one. All right, we'll say 565. Or for absorbance, it would be the highest point, which will also be 565. Okay. Now, you could use any other number if you want, but you're going to get the best results with 565. What are you going to do next? Now, the next thing you're going to do, you're going to remember that wavelength. Now, in this lab that I'm giving you, we're not going to use 565, I think. Let me see what it says to use. Oh, you know what? I think I could figure out what it would be. What is the one that we used? I'm pretty sure we used a blue color. Yeah, I'm almost certain we used blue because it's an orange solution. It's a reddish solution. So we used blue is 470. Okay, so let's just say that that you did the experiment. Well, that means that, okay, I got to change it. Well, I can change it around. Hey, I got some other chalk here. Oh, no. Do I have it? Yeah. Okay. So I'm going to put this. Kind of an orange and a red color. So hopefully, yeah, that looks reddish-orange now because this has iron in it. So this experiment, if we were able to do it in person, we actually use, okay, let me tell you how it works. So I actually have both of these to show you. We actually use iron solution. And it tells you in the experiment that we're going to have iron plus 3 chloride. Iron plus, it will look like this, okay, really dark. But then we're going to add some other chemicals. One's an organic chemical because it turns out better if we slightly change the color for whatever reason. I don't know why. We could have just used orange. But they decided to add some chemical, and so it ends up looking more reddish color. So instead of being orange, it's kind of between these two. It's kind of a reddish color, the one you do. A reddish orange. Now, for reddish orange color, if we go back to the color wheel, it turns out that the color that it absorbs the best is not green, but is a blue color. Maybe a greenish blue, actually. It's kind of good if I put that. So then that's the one that just barely will pass through. A bluish color, a bluish green color passes through. Oh yeah, maybe it's a cyan, like I was telling you on there. Kind of a cyan color passes through, and a very little of it comes out. That is the optimal wavelength, 470 nanometers. That's the one that we will say that you use for this lab. Now you're not going to have to. Well, if you did the experiment, we'd say, okay, set it on 470 nanometers. Or if it, if it had been the green light, you set on the one I showed you, 565. All right, what's the point? So I'm gonna set my little this little colorimeter or spectrophotometer on 470 nanometers. That means only a bluish light will shine through, a blue, like a laser pen blue light will shine through what you saw on the others. Now, let me tell you a little bit about the procedure. And I got to tell you about the procedure first, and I'll get more of the math. Okay, so what you do in the procedure, you're going to take a cuvette. You're going to take this, and you're going to put distilled water in it, completely pure, nothing at all, completely clear. And you're going to put this in as it's set on 470, and you're going to line this up. They always tell you, don't touch the sides of this, because your fingerprint, if you put a fingerprint there, then the blue light's going to get blocked by the fingerprint. You don't want the blue light to be blocked by your fingerprint. You only want it to be blocked by the solution. Okay? So you're going to put it there, and you're going to put it inside, and you're going to measure now. This is called calibrating it. To calibrate it, you're going to say, okay, I'm going to push the cal button, calibration, and when you push that, it will say that you have a transmittance, or absorbance is 0. Yeah, it'll be a 0 absorbance. Or either 0 absorbance means, I'm sorry. It'll be 100%. It's 100% transmittance. I'm so sorry. When you put in the blank, press calibrate or the 0 button, and you'll see that transmittance, this makes sense. You're saying that when blue light shines through, transmittance should be 100%. Yeah, did I say that? Yeah, because if you have pure water in there, all the light will pass through. So it'll be 100% transmittance, and your absorbance will be 0. Okay, maybe I was saying it right, and then as I thought it through, drawing it, I corrected myself. So when you go through distilled water, the very beginning, you push the calibrate, distilled water, you 0 it, and that means all of it is 100% transmittance is on there. And the absorbance will be about 0. Okay, now what's going to happen is you're going to take the reddish orange solution that I told you about, and you're going to put some in that container, in that cuvette. But it's not going to be just this one. What you're going to do is, let's say that instead of having one cuvette, one of them, you have like 10 of them. Or in this lab, I guess you have 5 of them. And each one of them, you're going to put a little bit of this and then some water. A little bit water, a little bit water. They're going to get darker and darker, well, lighter and lighter. So you start with dark, darkest, lighter, lighter, all the way to the lightest. So you have many different colors. Okay, that's what you have to do. You have to have 5 different cuvettes. 1, 2, 3, 4, 5. And then you have a blank also. The blank is just pure water. And then each of these are going to have different shades of the red in there. I guess I'm not going to color it in. It'll take me too long if I do that. But you can imagine from lightest, well, why not do a little bit? I'm talking to myself. Okay, so like I might start with one that's like really, really light and get to really, really dark over here. And then kind of like in between, something like that. And then we get the orange stuff. Oh, it's fun to play with the colors, isn't it? So that'll be like the darkest, and that'll be very light. I don't know. That's not doing too good, is it? Well, oh well. Oh, I can do this too. That'll help it. Oh yeah, that does too much. Well, anyway, I'd mess it up now. It's supposed to be getting darker as you go across. So lightest to darkest, nothing at all, then lightest to darkest. So you make 5 different solutions. Now, here's the one part that you might not like so much. I'm going to get to this in a minute. You have to know this lab for number 1, number 2, number 3, number 4, number 5 test tube or cuvette. You have to know the molarity in each one. You have to calculate the molarity in each one, and you do that with M1V1 equals M2V2. You have to do that 5 times to find the molarity of all of them, or 6. Maybe it's 6 in here. We'll find out in a minute. So I'm going to make 5 different ones. I got my color. The solution's red-orange. I know that blue light, we said it was 470 nanometers, is set. First, I put in a blank, and I push the 0 button. Then, after pushing the blank, getting the 0, now what I'm going to do is I'm going to put in one of these colors and test and measure what is the transmittance and absorbance. I only care about the absorbance. That's all we're going to graph. We're going to measure for, actually, this is on your lab. I keep saying it here, but let me show you where it is on the paper. And yeah, actually there are 5 test tubes. They're on this last page, this one right here. There are 6 test tubes. Well, 5, and then B is the blank one. And it says, what's the molarity inside each one? You're going to put the molarity here. And of course, it'd be 0 for the blank, 0 molarity. And the absorbance, you'll read off the machine on the computer, and it will tell you the absorbance values will go for test tube number, well, test tube or cuvette number 1, 2, 3, 4, 5, blank. We know that for the blank one, the molarity, concentration, and then here we'll put the absorbance. Concentration for the blank is 0 and absorbance is 0. But all the other ones, you're going to have to calculate what are these molarities. And then for the absorbances, you're going to have to measure them on a machine. Now, I'm going to give you some values in a moment for you to use. All right, so let me go back to my my first page. Is there anything here I want to show you? Yes, okay. I got to go back to this one now about Beer's law. Now, this one says A equals ABC, but now they use epsilon instead of the small a. I guess having 2 A's was too much of a confusion here. So I'm going to measure 5 different reddish-orange solutions. One of them is very, very weak and light, small molarity. One is very dark, high molarity. I'm going to always put in the same color of light and see how much is, well, really I only care about absorbance, which is a logarithm of the fraction that gets through. So you saw that from the formula on the first page. You don't have to even know you don't need to know the math formula for absorbance, but it'll be a fractional number. The transmittance, I mean, you see that a lot. You don't have to graph that though. Okay, now I'm going to do that each time. Every time you put in a new test tube, you put it inside this. You have to inside this. Every time you have to first put in the blank, then press 0. Not the calibrate. You calibrate the very first time, but then you can just push. Well, I guess it is calibrating, but the 0 button. Think about the 0. You push 0 each time with the white. Yeah, you do calibrate it. It is calibrating again, and then you put in number 1. Then put in the blank, calibrate number 2. The blank, calibrate number 3, and so forth. And every time you do it, you make sure you put it. You open this up. You put the cuvette inside, the blank one, for example, calibrate. All right, after you get the value right, you write down the value. Well, you don't write down anything from blanking it. Then you take this out. Now you put in the red one. Then you close it and don't push calibrate, and then just read what the number is. Take red number 1 out. Now I got to put in the blank again, calibrate it. Okay, now I'm ready for number 2. I'll take that one out. I'll put in number 2. And I'll measure number 2. What is number 2's absorbance? 1, 2, 3, 4, 5. That's how you do it. Okay. Now there's going to be a little bit of math here. Well, there is a couple of math things I'll have to show you. But first, I'm going to show you the how to get the absorbance here. Okay. When you get your numbers, like it says here, the Beer-Lambert plot, you're gonna graph. Beer-Lambert is when you graph absorbance versus the concentration. So down here's a molarity, 0 molarity to, and actually they're going to be very small molarities. So I could put 0 to 3.00, but here's what I'm going to say, times 10 to the negative, I don't know, what did I have on one of these papers? I don't even know if these numbers were right that I had on my paper. Oh, 10 to the negative 3. Sometimes they'll write concentration times 10 to the negative 3, and you have a 3 there. Actually, it should be more than 3. Let's put a 9 there. Okay. Well, how about 10? I'm crazy. 10. Well, 10. Okay, I'll just put 10. So what that means is when you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it's really 2 times 10 to the negative 3. So it's really 0.002. So 0.001, 0.002. But it's kind of hard to fit that under the graph. So sometimes they'll go 1 through 10, and they'll put times 10 to the negative 3 below it. Okay. But absorbent. Okay, anyway, when you graph these two, you're going to get some dots. Now, this is something I want you to be aware of, a science skill in physics, chemistry, everything. When you graph your points, they might not be perfectly lined up, all right? They might look like that, like a little bit off. One could be really far off. I'll just put it there. Well, so what you should do is always circle all the dots. Then what you should do is find a straight edge. Oh, I can actually use the periodic table. And you want to line up as many dots as you can to be on the line. And you want to have an equal number above and below. So it looks like somewhere around here would be my best straight line. Now, notice I've got 2 dots above the line and kind of off, and 2 that are below the line, and those circles are pretty much on the line. That represents an average of all your data. That's the way you're supposed to do it when you do it by hand. Okay? Now, if you had one point that was way off like that, you would just ignore that point when you're doing it. Oh, something happened, somebody sneezed, or they put it in too fast, or they didn't calibrate it, or whatever. But anyway, that's how it goes. Now, once you find that graph, then here's the cool thing: the slope. Calculate the slope. Now, can you remember that slope is always a change in y over change in x, or in this case, change in absorbance over change in molarity or concentration. So I'll take 2 points. Now, what you want to do, I don't have it done too well here, but you want to look on your graph paper somewhere, and you want to look there's a bunch of little squares will be on it. I always wonder if they're ever going to do this on the AP exam and make you do this. They have made people do graphs, but let me just put one right there, for example. Oh no. Put one there, and maybe I'll put one right here. Okay, so here's what you want to look at on a graph paper. You want to try to find 2 places where you come right through the intersection like that. Let's say across of 2 lines, and your line goes right through it. Like here's one right there. Now notice at this point, I drew it, and I made this on purpose, but I'm saying it will naturally happen. So this would be a very good point to use. Whatever that, at 1 and whatever that is, absorbance. That would be a good point. We'll call that x1, y1. Then you go up here, and look, there. What do you know? That one comes out to be, here the line intersects exactly through a cross. See, right here it doesn't. Here it's only going through this one line. That's not a good point. That's not a good point. That's not a good point. That would be a good point also. But take 2 as far apart as possible, and that'll be x2, y2. Okay, so now you know x1, y1, x2, y2. If you want to call it concentration 1, absorbance 1, concentration 2, absorbance 2. But you read the 2 points, you write them down, then you do the change in y or change in x is y2 minus y1 divided by x2 minus x1. When you can all find the slope of a line, that's easy. Guess what? When you find the slope, that is equal to the molar absorptivity constant. That is the epsilon here. So every lab will have the chemical, depending on your molarity. Well, actually, no. Depending on the color of the solution, actually, will have its own value for that. And actually, if we did an experiment, for this particular experiment, yeah, they could all be a little bit different because you're altering the color a little bit. They might all have a different constant, but you find the molar absorptivity constant. You find that out. Once you know this constant, now you can make calculations with A, B, C. Okay. So let me go down at the bottom of this, the notes page I have. There's a little example problem. I'm going to do that one right now for you. Then there's one more math thing, and so I know this is a lot. What in the world? But yes, this is something that AP wants you to know how to do. Okay, so here we go. So it says on the example, It says, in experiment, I'm doing this example near the bottom of the page here, in an experiment. In an experiment, the molar absorptivity constant is determined to be, and it says A equals 0.179 liter over mole -1 centimeter -1. Kind of weird how they write the unit, but don't worry about that. But that's just how they write it. And now this is an older version, so now it should actually be the constant epsilon. So not A, but epsilon, the constant is equal to that. They determined that from a lab. They did the whole lab and they found that constant. Now A says, calculate the concentration of a sample that has an absorbance of 0.570. So what you do, once you've made the graph and you found that point, now you're going to say, okay, what if we know, let's just say that you did your lab, your 5 different colors, okay, and you're done with the lab and you found that constant. Then I walk in, I say, okay, guess what? I have a new solution for you to check, and it's a color that was not 1, 2, 3, 4, or 5. It's a really light colored liquid solution in between those somewhere, and you don't know where. And I'll say, put it in, and I'll say, here's one, test it out. What is the molarity of this red solution? So after you've done your lab, you found that constant. Then I get some in a container. I said, hey, tell me the molarity of this one. And you go, okay, what is that? So you put it in the machine, and it reads it tells you, oh, I'm sorry, that's not true. It says, I'll calculate the concentration. The absorbance is 0.570. So say you put it in the machine, and the absorbance is 0.570. What is the concentration? Well, this is so easy, I hope. 0.179. If you want to write the units, you could. Remember, I liter, mole, cm on the bottom. Kind of like the R constant a little bit with the units. B is 1 centimeter pretty much always. They'll tell you if it's something different, they'll let you know. And C is the molarity of the concentration. We don't know. What is the molarity of this? If it's 0.570 absorbance, well, then I'll say, well, my centimeters cancel. And, of course, I'm going to divide both sides by 0.179. Actually, by 0.179 liter over mole. If I divide that by 0.179 liter over mole, you don't have to write the liter mole part, but it's going to flip it to mole per liter. So 0.570 divided by that, it's 3.18 mole per liter is the concentration. So again, we brought in a red solution when your lab was all done. You already had done your graph. You calculated the constant. We brought in a new red one and said, okay, let's measure this. Oh, it's 0.570 in the machine, in the computer. So what is its molarity? And you just plug it into this. And you say, oh, it must be 3.18 molar. Okay. All right. And then there's another question after it that says, what should be the absorbance of a 2.80 molar? So now you might say, okay, I'm going to make a solution that I know has a molarity of 2.80 mole per liter. What should the absorbance be? Well, I'm just going to calculate the same thing, 0.179, liter, mole cm times 1 cm. Just calculate it, and it looks like it's 0.501. 0.501. There's no unit for absorbance, so it'd be 0.501. That's all you put there. Okay, so that's how you do that math. So now, as far as the lab, what do I want you to do? Okay, so I've done that first little bit. On the pre-lab, on the next question, letter A, number 1, I want you to tell me what is Beer's law. Answer that one. Number 2, you don't really have to worry about serial dilution because when we do the lab, I don't have a serial dilution. But I'll tell you what it is though, just in case you want to know. Let's just say that something is 5 molar, a solution. So a serial dilution might be like, just say I've got 5 milliliters of 5 molar. I'll take another test tube, and I'm going to put 2.5 milliliters of that one, and now I'm going to add water up to the top until I get to 5. So by 2, so it'd be 2.50 molar. So in other words, I take this first solution, I put half of it in here, add water for the other half, and I diluted it. Then I'm going to take that one and pour maybe halfway into this solution and dilute it up, and then on. So that way I get many, many, many different solutions of different molarities to check. That's one way to do it. But I decided when I did the lab to not do it that way. And I'll give you some different directions. I'm going to talk about that in a minute. Number 3, you know what? You don't have to even do number 3 either. Just do number 1 and number 4. Okay. Oh, and I kind of told you that already. Oh, no. Well, that's all right. Oh, no, I didn't completely, but I sort of did. You can do either way. Okay. All right, now, on the procedure, it says label 6 test tubes, 1 through 5, and a blank. So you're not going to actually do it because we're not there. But all right, you have 6 test tubes. So you might draw it out to kind of help yourself. You got 1, 2, 3, 4, 5, 6. So 1's a blank. And all right, now it says you're going to have dilute 1 milliliter of iron 3 chloride stock solution to 10 with deionized water to make 0.01. Transfer 1 milliliter of 0.01 to test tube number 1. Add 5 milliliters. Transfer 1 milliliter of that to test tube 2. Add 5 milliliters by vortexing. Vortexing means you kind of move it around like this. Like I would be vortexing it if I did. Well, I'd hold this one. Shaking it up would be that, and it'll all splash out into the air. Okay. Stirring it would be putting a stirring rod. We don't want to touch anything inside there; it might affect it. So vortexing just means you're doing this, like a small amount in a big test tube. You're doing that. So you're like stirring it. They call it vortexing. Okay. Add 5 drops of phenylethylamine, 1 milliliter acetate buffer. All these chemicals were added to change the color of it. Oh, it said to use 512, not 470. Well, it's okay. I don't know if mine has 512 on it. I don't think it. No, mine doesn't have 512. 470 is the closest we could get to it. So we did use 470. We're not really doing the lab anyway, though. Okay. Then on the calculation, you can do number 1. Yeah, you better just use what the data for number 1, number 2. Calculate concentration. Okay. All right. Calculate the molarity in each test tube. I need to kind of help you with that one on number 3. How can we do this? Okay. Under the procedure, number 2 and number 3, 2, 3, and 4 are not going to affect you. You don't have to worry about the molarity on those. You're just adding stuff. You're not changing. Well, we're going to find the molarity. Yeah, you're going to end up having 6 milliliters total. Let me check where I have mine. I cannot believe this. I don't have my... I might have to give you that data. Oh, okay. Oh, hold. Oh my goodness, you guys! I'm so sorry. I have the wrong. I was looking at the wrong lab. I mean, an older version. No, not that bad. Okay, here's your lab procedure. It's a little bit different. Number 1, level testers 1 through 5. B for a blank. Measure 5 milliliters distilled water to the grad cylinder. Pour it. Okay. Get 2 grad cylinders. 1 milliliter of 0.10. Add distilled water as a total volume to make 0.10 molar solution. Oh, this is going to be very easy. I'm so sorry for taking a little bit of time, but okay, here's the deal. On the procedure, I want you to read through it as if you were doing it so you kind of understand it. But here's the bottom line. Before you get to number 2, all right. Number 2 talks about how you prepare test tube number 1. All right, but here's what you're going to do. Let me say, so here is number 1, number 2, number 3, number 4, number 5. Watch what I'm going to show you here. I'm sorry if that kind of got you messed up. But here's the deal. Number 1, I explain how to prepare number 1 on number 2. But before number 2, right before it, here's what they tell you. You're going to have a cylinder. I'm just going to have a graduated cylinder. And in that cylinder, I'm going to have 0.010 molar of iron plus 3. Really, yeah, it's going to turn into iron plus 2, but that won't even matter. I'm not going to mess you up with that. But I have 0.010 molar of this, and I've got okay. Let me color it for you too. This is not going to be hard. It's just I'm having to think it through, and it's weird for me to not have the chemicals with me. You know, I would have prepared the experiment in class, and I'd be like a little bit more fresh and sharp on this. Almost done here anyway. It's going to be a long video, I know. Okay, here we go. I'll put that one here. Okay, so here you've got. This is really where you can start the math of the lab. Okay, I've got, this is the very bottom number, this is number 4, number 1 part 4 on the procedure. 1 part 4 on the procedure is right here. You have 0.10, well I'll put the top there. You have 0.10 molar of iron 3 in a graduated cylinder. Let's just say you got 100 mil, it doesn't matter. I got a lot of this, okay? Now what I'm going to do, I'm going to take a pipette. Oh, I can even show you that as well. Or I can use a graduated cylinder, that's okay. This is better. I'm going to use another graduated cylinder. I'm going to take out of this, it says, look at number 2. Now, start here. Here's what you have, 0.010 molar iron plus 3 solution. Okay, I'm going to take out, on number 2, 1 milliliter of this. So I'm going to put this little pipette inside, siphon it out, and put in here 1 milliliter into a cylinder. Not into, you can put it there, but I'm going to put it in here first. Okay, I'm going to put 1 milliliter. I can draw it here, because it's not going to hurt you. I put 1 milliliter of this into there. Then it says, add water until the total volume is 5 milliliters. Okay? So I'm going to add more water until it gets all the way up to 5 milliliters. Boom. 5 milliliters. This is water. This is 1 milliliter of this, and that's up to 5 milliliters of number 1. Okay. So I put 1 milliliter into number 1. Oh, let me do it this way. From here to there, 1. Then for the next one, it says step 3, transfer 2 into test tube number, we'll go to 3. 2 of them will go into 3. We skip 2 for a minute. 2 milliliters. And then 3 milliliters will go into number 5. So we're skipping around a little bit. 3 milliliters go into there. So 1 milliliter of this into here. 2 milliliters of this into there. 3 milliliters into there. And then you put what? 1.5, 2.5, and 1.5 in the others. It tells you step 2, 3, 4, 5, up to 6. Okay, now in your math or homework, you got to calculate what is the molarity in each of the test tubes. Or each of the cuvettes. The way you do that is M1V1 equals M2V2. Yeah, you got to do it 5 times. But I'll do the first one for you. The first one, we took 1 milliliter of 0.010 molar. That means I had 0.010 molar, and I only had 1 ml. Now remember, that's a shortcut, keeping the ml there. The final M, we don't know. We're trying to find it, and we're doing for test tube number 1. The final volume was up to 5 milliliters. So 5 milliliter and 1 milliliter are going to cancel. And so 0.010 equals 5m. And so it's X is 2 times 10 to the negative 3. So M would equal, divide both sides by 5. I've got it written down here. It's going to be 2.0 times 10 to the negative 3 molar. That's for test tube number 1. All right. Test tube number 1. And then you got to calculate for number 2, number 3, number 4, number 5. All of them. Blank, you don't have to do it for that. It's just 0 molar. All right. Then take those numbers, and on your next page, there's a list of test tube number, concentration, and absorbance. I'm going to tell you the absorbance values. I'm glad you held on this long. Test tube number 1 is 2.0, 10 to the negative 3 molar. And the absorbance, we'll just use these numbers that I'm going to give you right now. We're going to just let everybody use this. It's going to be like a worksheet. 0.10, 0.21 is going to be number 2. But you got to calculate it, of course. You got to calculate the molarity. 0.21 when you put in number 2. Number 3 is 0.33. Number 4 is 0.45. And number 5, the absorbance is 0.54. And the blank is 0. So I'm going to get one. I got that first one for you. You got to find number 2, 3, 4, 5. You got to find these molarities. Then you need to graph them on the graph on the next page, and then finish the other questions that are on the paper. So I did a whole lot of this for you. I know it took me a long time. I'm going to give you a little bit longer time to do this as well. So this will be fun. And now you got a lab of Beer's law and you'll figure out. Yeah, well, just go through it, and then we'll talk about when it's over with everything. I'll see you guys.